So today's topic is relative velocity. So we'll learn about what relative velocity is, how it can be correlated in terms of normal velocities, and then we'll try to see some examples, a couple of examples in order to figure out, what is the usability of this theory. All right. So, so yeah. So for today's topic, we'll be doing relative velocity as part of our lecture 2. And what we are trying to do in here is to first define what relative velocity actually is. All right. So let's say there is a frame of reference. Now, what you mean by frame of reference? So let's say I am running at a velocity of v. Okay. Now my wife is running at a velocity of u. As you can see from my stature, I'll be probably moving at a smaller velocity than her velocity because she goes to gym and whatnot. So, so in the ground's frame of reference, for a stationary person, they will see me moving at velocity v and my wife moving at velocity u, or running at velocity v and u respectively. So here is me, here is my wife. Now, if you ask me, the situation will be very, very different. To me, I'm already moving at a velocity v, so I will see my wife moving at a velocity which is offset compared to my velocity, since I'm running towards her. So think about this. If I have covered in time t, in delta time t from my start, a distance x, then my wife with respect to this ground observer, so we'll say it with respect to ground observer, my wife with respect to that ground observer has moved the velocity of u. So with respect to me, she's only ahead of me this her distance from the origin, which is x, the wife with respect to ground, and x me with respect to ground. So this distance, if we take off this distance from that distance, that is how much my wife is ahead of me. So delta x of my wife with respect to me is u delta t minus v delta t, where u is greater than v. So it becomes u minus v delta t. So the relative distance of my wife with respect to me is u minus v times delta t, and that gives rise to relative velocity of my wife with respect to me, which is defined as delta x of wife with respect to me divided by delta t equal to u minus v. Right? So that concludes how we can calculate relative velocities. Now, this relative velocity is the case when we are moving in the same direction. If we are moving in the opposite direction, let's say we were not getting along and we started moving in our different directions. So if you do this case, let's say we started at some origin O when we had a disagreement between the two of us, and there is a person who is at that location and he started measuring the distance traveled by me and my wife. So in his frame of reference, my wife has moved positive x with respect to ground of u times delta t, and me, I have moved in a negative x direction, assuming this is positive x and this is negative x, a distance of, because he is a ground observer, he is not moving at all, a distance of minus v times delta t. So with respect to me, when I'm here, the absolute value of the distance delta x y with respect to me is actually u delta t minus v delta t. So it is u plus v delta t. So relative velocity of my y with respect to me is u plus v, given by delta x of y with respect to me divided by delta t. So hope this is clear. So the concept is, if we are moving in this, if two bodies are moving in the same directions at velocity v and u respectively, then in this frame of reference, for the body which is ahead of this one, the relative velocity is u minus v. The body has to be just ahead, and depending on the difference of u minus v, if v is bigger than u, then you will, if you were running faster than your wife, then it would show as if your wife is moving towards you, because the directionality of u minus v will be negative. So physically, if u is less than v, then it would seem, although you guys are moving in the same direction, with respect to you, your wife will be moving towards you at a speed of v minus u, because v is greater than u. But if your wife is faster than you, which is the case in my particular scenario, then if u is greater than v, then your v minus u will be, then the velocity is u minus v, and it would look that your wife is going ahead of you at a speed of u minus v. Now, the other if condition is, if you and your wife are moving in opposite directions, then the sign does not matter. You will obviously see her going away at a speed of v plus u, and she will also see you going away at a speed of v plus u. Alright? So that is this part of the lecture, just from an understanding point of view. Just from an understanding point of view, mathematically how we tackle this problem is very, very simple. What we tend to do is, and I would like to give a couple of minutes for you guys to capture what is written on the board, and if you are taking any notes, so I would like to give that time to you. And if you guys have any questions, please just leave a comment in the comment section. Since I'm doing it for fun, I will not press you for be a subscriber or do a like on this particular video, but if you would like to do so, please go ahead and do that. I would just say that, if you have further questions on what relative velocity fundamentally means, leave a comment in the comment section, and you can also ask questions. I'll give you an email the next time, the email where you can ask me questions the next time. So that's about it from a physical understanding of relative velocity. If two bodies are moving in the same direction, then with respect to one body, the other body is moving at that velocity, their own velocity subtracted with the other body's velocity, and if they're moving away from each other, the velocities do add. Alright, so this is the way of doing it. But let's say you have, and I guess you guys have taken notes of this particular particular concept in here. So we'll move to the next part of the lecture, how you tend to do it mathematically. So how you tend to do it mathematically, you don't want to get into all this. If there are two bodies moving in three dimensions, let's say one projectile, let's say you have, now in US people use a lot of hunting guns and things like that. So let's say, and I do not want to put my opinion whether I am for or against hunting, but let's say there is a gun, air gun, which has shot a projectile in this direction, and then they moved their gun, angled it at a certain angle, and then at a later time instant, so this is at t equal to 0 and time t equal to t, later instant fired another projectile, uh, and but that time this new projectile has a velocity v, and by that instant of time this older projectile has gained a velocity of u. Now it's in 3D, and it's very difficult in 3D that you can figure out whether the bodies are moving towards each other or they're going away from each other, and things like that. So generally speaking, what you tend to do is you tend to project the u's and v's, because these are vectorial quantities. You tend to project them in their respective um, x, y, and z directions. You write them as ux I cap plus uy j cap plus uz k cap, and you write this velocity as vx I cap plus vy j cap plus vz k cap, right? And then you just take the difference of one vectorial quantity with respect to another, and I'll prove to you that the velocities will still add in the simple case when my wife and me were going in the opposite direction. So wait for that. So in this case, at least, if you do this, then your velocities will come out to be ux minus vx I cap plus uy minus vy j cap plus uz minus vz k cap. Okay, so in three dimensions it's a much easier way of calculating the relative velocity of one body with respect to another. And you have to always remember, for this case particularly, since u is written in front and v is written after subtraction, so basically if we call this body as a and this body as b, then we are calculating velocity of b with respect to a, and this is the way of writing it. vba, velocity of b with respect to a, is u minus v, velocity of b with respect to, so velocity of b minus velocity of a, which in turn is, since velocity of b is u vector and velocity of a is v vector, so that's how you are going to tackle this problem. So I'm going to give you another minute in order to capture whatever is written on the screen if you want to, and we'll go and prove that if both of us are moving in the opposite direction, although there is a negative sign involved, the velocities do add with respect to one another. Okay, because that's what we saw from a physical standpoint, and we have to fit that physical theory into a mathematical construct. Okay, so I hope we are able to write and understand what I am, as I showed you the physical and mathematical constructs of relative velocity here in this case. So what that would mean is that let's come and try and solve that particular problem where me and my wife were moving into opposite directions. So okay, if we assume that this is positive x direction and I started moving in the negative x direction at a velocity of v, then my speed with respect to the ground observer here is minus v I cap. I cap is the notion of unit vector in the minus x direction. Okay, so minus I cap is. And my wife, on the other hand, she is moving in the positive x direction at a velocity of u. So u of wife is positive u I cap. Okay, so now according to the concept which we mathematically described just in the last when I was writing stuff for the mathematical construct, if you would like to define velocity of y with respect to me, that will be velocity of y minus velocity of me. Velocity of y is u I cap, velocity of me is minus minus v I cap. So that would turn out to be u plus v I cap. So you can see that the velocities still add when you are moving into opposite directions. So with that, I would like to conclude the theoretical aspects of relative velocity. In a moment, we'll try and solve an example on relative velocity and go forward with our next lecture, hopefully. So again, just ask me your questions. I would be very glad to answer your questions. And I will see and try to figure out a time where we can, if I find time over the weekend or somewhere, we can devote some personal time, if time permits at all with respect to me. So with that, this section of the lecture on relative velocity concepts is now done, and we'll move on to a numerical example next. Thank you. Alright, so now we are ready with that example. Yeah, so that is the first question of the book written by Irodov, Problems in General Physics. I guess it used to be published by Mir Publishers back when I was preparing for this examination. Alright, JE. It used to be a very cheap book. Still, it continues to be a very cheap book, but the questions in there are some of the best questions I have seen so far. So the first question talks about there being a motorized boat. Okay, let's say the motorized boat's velocity is Vm. Now, if the velocity, the motorized boat's velocity is with respect to the water on which it is traveling, right? So, if the water is downstream, then it will have certain velocity. But for the motorized boat, at a certain engine duty, the velocity will continue to be Vm, right? For a person who is inside that motorized boat, will calculate velocity of motorized boat with respect to water, and he will say that okay, this velocity is, let's say, Vm. Okay. Now, if and in that question, it is said that the the stream is actually downstream in nature. Okay, so the velocity of water with respect to ground is plus um, let's say plus v I cap. This is Vm I cap and this is plus v I cap. So velocity of motorboat with respect to water is Vm I cap, and then the velocity of water with respect to a ground observer over here who is on the river banks or things like that, he's saying that the water or the downstream is itself moving at plus v I cap. The idea is to find out the stream velocity or velocity of the stream. So how this question is framed is that there is a raft which does not have its own velocity, obviously. Um, so So this observer on this motorboat sees the raft person with, let's say, sunglasses and whatnot. Looks like a nerd, but he could be a very dashing personality in there. So this is moving downstream, and the raft person is in no hurry. So the velocity of raft with respect to water is 0, and velocity of water with respect to ground continues to be plus VSI cap. So the question so the problem goes further, and it is said that after traveling in the forward direction for plus 60 minutes or an hour, this guy over here who is in a hurry, maybe to make more money in his life, so they are at point A when they saw each other. This guy in an hour goes to some point B, let's say to collect money, or if he's a James Bond, where to collect something else. They go from point A to point B, and then they collect whatever they need collected in no time, relativistic physics and things like that. And then he starts coming back, and this raft guy who is moving at 0 velocity with respect to water, obviously because of the speed of the stream, goes forward in time, still with sunglasses on and things like that, smile on the face, goes to a certain distance, and that distance will be certain distance, let's say D, and for the boat which is coming back, now when the motor boat will be coming back, they will see an upstream flow with respect to their boat, right? So the motor boat will be certainly moving ahead in the negative Vm I cap direction, but so this is velocity of motor boat with respect to water, but the stream as such, velocity of water with respect to ground, will continue to be in the plus Vs I cap direction. So this is the entire question. Okay. So yeah, let's start putting things together. So let's say this from here to here is, so let's forget about 60 minutes, 1 hour and things like that. Let's talk in terms of abstract numbers first. So the time for going from point A to point B is, let's say, some time given by TAB, and then when the boat starts to come back is the time TBC, when the boat guy who is in a hurry will start seeing the raft guy again. Okay, so in TAB amount of time, first of all we need to, because everything is getting calculated with respect to this ground observer, so we have to calculate first velocity of motorboat with respect to ground, because for me or for a certain person whoever is on the boat, they will not notice at what velocity the water is going, whether it's downstream or upstream. They will just say how much is their motorboat's velocity, right? So velocity of motorboat with respect to ground when it is downstream is can be written as velocity of motorboat with respect to water plus velocity of water with respect to ground, right? Velocity of motorboat with respect to water is Vm I cap, and the velocity of water with respect to ground is Vs I cap. So velocity of motorboat with respect to ground becomes Vm plus Vs I cap. Similarly, when the boat is coming back, so the total amount of distance XAB, which the boat will cover, is Vm G times TAB, and that will be VM plus VS uh, times TAB, right? So that is the amount of distance this boat has traveled, and we know that that time TAB is 60 minutes or 1 hour, but let's not look into that for now. Then let's calculate velocity of raft with respect to ground. So velocity of raft with respect to ground is velocity of raft, with respect to water plus velocity of water with respect to ground. So velocity of raft with respect to water is 0, and it continues to be in the downstream direction. So velocity of water with respect to ground is anyways plus Vs I cap. So we get velocity of raft with respect to ground is Vs I cap for the entirety of time AB and time BC. Okay, so this distance which the raft has moved is x is d, which is velocity of raft with respect to ground times TAB plus TBC, which in turn is Vs times TAB plus TBC. Now when the motorboat is coming back, so this is going forward downstream direction, when the motorboat is coming back, the velocity with respect to ground might have changed, and how it has changed is now the velocity they are seeing is minus Vm I cap. So again it will be velocity of motorboat with respect to water plus velocity of water with respect to ground, and everything has to be done with respect to the same observer. So the velocity of the motorboat now is minus Vm I cap plus Vs I cap, because the water continues to be in the positive x direction. So we got Vs minus Vm I cap. So while coming back, so this distance xbc is Vs minus Vm, so velocity of motorboat with respect to ground in the in the upstream flow times TBC. So this is Vs minus Vm TBC. All right. So these are the few things which we are dealing with at this point in time. So basically now let's forget all our characters with sunglasses and James Bond and things like that. What we are, so I'll give you a couple of minutes to look at this entire thing over here. So yeah, the thing which I was talking about. So basically, once you have written down the essential aspects of the problem and you have converted the verbiage of the problem into proper math, your constructor part is over. You can take out all the funny characters and just keep the main points on the board and things like that, right? So that's what we are going to do here now. So basically what we'll do is this distance which the raft has traveled, distance d plus xbc, should equate to the distance which the motorboat has traveled in the forward direction. Okay, so this distance is this distance plus how much the raft has traveled. So in order to do the math, it's pretty simple, I would assume. So we can do it together pretty fast. So yeah, let's start putting things together, I would guess, and let's go from there. Okay, so again, you know, so yeah, that's what we are going to do now. So this will be Vs TAB plus TBC plus uh, Vs minus Vm TBC equals Vm plus Vs TAB. So basically, it essentially boils down to this particular problem here, right? One thing which I'm just thinking about is that, you know, when the boat is coming back, it's actually traveling in the minus x direction. So although we have calculated this velocity, this relative velocity in plus I cap direction. So this should be ideally cap or Vm minus Vs minus I cap. So we should use this velocity Vm minus Vs here. Okay, so now we have equated how much the distance motorboat has traveled in the downstream direction equals how much distance motorboat has traveled in the upstream direction. Added that to the raft's movement in the total time the motorboat has gone in the downstream and then came back in the upstream direction. Okay, so that's what we did here. So let's start putting things together. This is Vs times TAB plus Vs times TBC plus Vm times TBC minus Vs times TBC equals Vm times TAB plus Vs times TBC Vs times TAB. Now since we have converted everything into equation, we don't need these other, you know, previous parts of the problem any longer. So I'm going to take them off, if you will, and then basically try to solve this problem. So Vs times TBC and this term both cancel each other. We got and then this Vs times TAB term cancels over here. So we got Vm times TBC equals Vm times TAB. And it was mentioned that the distance which the raft has traveled is 6 kilometers. So the raft has traveled Vs TAB times plus TBC, and the time it took for the motorboat to go in the forward direction is 1 hour. So TAB is given out to be 1 hour and D is 6 kilometers. Anyways, so we got these two equations here, one coming from conservation of distance and the other coming from the fact how much the raft has traveled in total time of TAB plus TBC with respect to the ground observer here. So if we have that with respect to the first equation, TAB becomes TBC is actually TAB or 1 hour. If we put this back in equation number 2, we already know that TAB is 1 hour given. So your becomes D is which is 6 kilometers is Vs times 2 hours, because TAB is 1 hour and TBC is another hour. So your Vs, or the stream velocity, which we are required to figure out, that becomes 6 kilometers by 2 hours or 3 kilometers per hour. So with that, I'm going to end this part of the lecture. I'm sure there are going to be a lot of questions in trying to understand what I did in this example. Please feel free to ask those questions. I will also put my email address either in the description section of this video, or I will orally tell my my email address in the next one. So we'll go from there. Thank you and have a great day. Bye.